All right, so in this video, I'm going to cover how the math under aim constraint works, and I find that pretty interesting to cover as the first thing, because it really helps understanding how matrices are structured. Because when building an aim constraint, you go through the process of actually building an entire transformation matrix. So I'll kind of explain things as I go. I might brush over some things pretty quickly. I'll have links in the description, of good resources on vector math and matrices and that kind of things. So let's start with defining 2 points. Let's put them over here. So that would be A, that would be B. Then we want to build a transform, or the matrix that make that transform, so that the x vector of our object or transform points towards B, so that its y vector kind of is perpendicular to x, and so that the z vector is just like another vector perpendicular to all of that. Let me just redraw x because it's not looking great. Cool. So we've got these 3 vectors, and let's actually write the matrix that would make that transform. So the first row would always be the x vector. So let's write x, y, x, z. Then the second row of the matrix would be y, x, y, y, and y, z. And finally, you guessed it, that's going to be z, x, z, y, and z, z. With these, we have a 3x3 matrix, but we are already encoding a lot of things. We are encoding the orientation of our object, simply because we've defined each of the vectors, right? And the relationship between these 3 vectors make up in like an orientation. I could build an object that pointed in that direction. We would have like the y vector in that direction and the z vector kind of going in that direction, and that would be a different orientation, right? But also it would be built in the same way. We would have the similar matrix with different values, and that would also, just encode the orientation of that object. Another thing that is encoded in a 3x3 matrix is the scaling of the object. So let's say we had that vector twice as long, then this would be encoded in this row, because we wouldn't have a vector that's length would not be 1, sorry. So the length of that vector would not be 1, but it would be 2, which pretty much means that the scale of our object on the x-axis would be 2. And if we wanted an object uniformly scaled, we would just scale all 3 vectors like that, and that would be our object scaled by 2 on all the x's. And the last thing that is typically encoded in a matrix, the 3x3 matrix, is the shearing. Shearing is not something that you typically use in rigging, but it basically is whenever 2 of the 3 vectors are not perpendicular to each other, that's what's called shearing. You typically want to avoid shearing, so you want to make sure that all your vectors are always perpendicular to each other, but there might be cases where you do want that. But that's also encoded in there because, again, we've just defined 3 vectors and we've stored them as they are in the matrix. So let's go back to that. And the last thing that we are missing right now is the actual position of our transform, which is just stored as the last row of the matrix. So y, and a z. Cool. So now we have all the information that we actually care about. We are missing one column, and that column is always going to be 0, 0, and 1. Yeah, you don't really need to care about what that column means. I know it's used, I don't actually really know what it's used for, or like how to leverage it. But I know it's used under the hood, like for matrix multiplication and that kind of thing. Again, not really important in all everything you're going to be doing with matrices. You're going to have that as these values. Cool. So let's actually jump into the math and solve these three vectors. So the first one that's easy to solve is x, because it's simply the vector that goes from A to B, and the way you define that is you subtract A from B, so B minus A, and that gives us the vector that goes from A all the way up to B. Since we want a normalized vector to avoid any scaling, we will normalize that, and that's our x vector. Now the next one we are going to compute is not going to be y or z, because we do not have the data for that. What we are going to do is use a temporary vector that's going to assist us in building the other two vectors. That vector in Maya is typically called the up vector. It can be any vector that is not collinear with x. So it cannot be this vector or this vector. Typically in Maya, you define a third point. Let's call it, let's put it over here and call it C. And you use that to build that up vector. I'm going to call it y prime. So like so. And I'm going to define it as C minus A, because again, we subtract the origin from the target. And this one doesn't really need to be normalized because it's not going to be used in the final matrix. It's just a helper to assist us in building those other two vectors. Like I said, this one can really be anything. You could simply define it as 0, 1, 0. And that would work in nearly all cases, except when you have, like, if B was pointing straight up in the world and A was at the origin, then x and y prime would just be collinear, and that would break the aim constraint for the reason that I'm going to just explain right now. These two vectors, x and y prime, make up a plane. Like so. That plane has a normal, and that normal is our z vector. So if we had y prime and x on the same line, then that plane would really be undefined because, well, there's an infinite number of solutions of planes going through a single line, where there's only one single plane going through two different lines or vectors at a time. So that's the reason why you always want that up vector to not be lining up with x. But yeah, let's actually compute z as the normal to that y prime x plane. And the way you do that is simply doing the cross product of y prime and x. The cross product doesn't give you normalized output, so let's just normalize that. And there is a good chance that we've got this vector instead of the one that we actually want here. The way you know that you've got the wrong vector is in your final transform. If you notice any negative scaling on the z-axis here, then this means you got the wrong vector. The simple way to fix that, and the actual way to do it, is simply just swapping these two values like variables, because the vector that you get out of the cross product depends on like the order you do the cross product in. So if that's wrong, we just use y prime as the first and x as the second. Yeah, that's just something to be aware of. I never remember what order the cross product needs to be, so I just do some trial and error, and yeah, that's about it. Now we have two new vectors, so x, which we've got from the beginning, and z, which we've just computed, that defines a new plane for us. And that new plane has a normal vector, which is y. Then we simply define it as x cross z. And again, we want to normalize it because just as we did with z, this is not normalized. And we might want to flip those two values because we might have gotten that vector instead of the one that we want. I'm pretty sure that we'll see whenever we jump inside of Maya, but I'm pretty sure that this one is right and that this one will need to be inverted, like the order will need to be flipped. But yeah, we'll see whenever we actually implement the math inside of Maya. Yeah, and I'll keep that with a question mark. Cool. So that's actually us done. We have everything that we need. The x vector is solved right here. The y vector is solved right here and not here, right? This is the final vector that we want as our x vector for our transform. And then the z vector has been solved over here. And finally, the position is simply the position of our point A. Yeah, like I said, I'll have links in the description that kind of go a bit more in depth on matrices, vectors, and that kind of things. But that's the gist of it. And in the next video, I'm actually going to start building that same math inside of Maya and have an actual aim constraint that we can actually work with. All right, I'll see you there.